we present plug-and-play diffusion features for text-driven image-to-image translation. In our work, we enable structure control in text-to-image diffusion models by extending them to image-to-image translation. Given a guidance image and a target prompt as input, we generate an image that fulfills the prompt while retaining the semantic layout of the guidance image. In our approach, we first pose the question of how is semantic layout information internally encoded in diffusion models. And once we understand that, we ask how can we control structure in the generation process. By analyzing the convolutional and self-attention features of the diffusion model, we detect feature maps that are dominated by the semantic layout information of the generated image. Note how semantically corresponding regions across images are encoded similarly. Based on this observation, we control the structure by injecting relevant spatial features and self-attention maps from guidance images generation into the target generation. Here are some example results of our method. In previous work, STEdit proposed to control the layout with the guidance image by noising it to an intermediate time step and sampling from the time step on with the edit prompt. This approach suffers from an inherent trade-off between layout preservation and deviation in low frequencies required by the edit, such as colors. Our method allows both accurate structure preservation and deviation in colors, thus fulfilling the edit. In prompt-to-prompt, they control the generation by freezing the interaction of a generated guidance image with its text when generating an image with a new target text, which allows them to retain the original content. Their method has limited structure preservation, while ours allows fine-grained control over the generated shape and layout, as seen in this example. Their method also requires aligned source and target prompts, while our method works with arbitrary source and target prompts. In Make a Scene, they train a generator from scratch which gets segmentation masks as inputs in addition to the text. This requires large-scale training, while our method leverages a pre-trained model and requires no training. In addition, their final model is limited to segmentation mask guidance and the labels it was trained on, while our method can work on diverse guidance images and arbitrary prompts. In our work, we consider Stable Diffusion as our text-to-image generator. It gets as input a Gaussian noise and a text prompt and is based on a U-Net architecture, where each layer consists of a resonant block, a self-attention module, and a cross-attention module for injecting the prompt. We start by sampling images and extracting feature maps from the generation process. For real images, we use DDIM inversion to get the initial noise. We do this on a set of multiple images that share semantic parts. We then group the feature maps by their layer and the time step and perform a principal component analysis on each group, which allows us to reason about the visual properties dominating the high-dimensional features. We analyze the features on different image sets and visualize the three leading PCA components as RGB channels. We observe that a specific layer in the decoder of the U-Net is highly dominated by the semantic layout information. As can be seen, for each image set, similar semantic parts share the same colors, meaning that their activations are similar across the images in the set. Recall that the decoder block of the diffusion model consists of resonant, self-attention, and cross-attention blocks. Particularly, the self-attention block computes the similarity between the spatial query and key features. The concept of self-attention is thus closely related to self-similarity, which has been shown to serve as an excellent structure descriptor in both classic and modern works. To visualize the self-attention of a generated image, we apply PCA on the self-attention matrix and visualize the three leading components as RGB channels. As can be seen, the self-attention matrix aligns with the structure of the generated image in all the decoder resolutions. Based on our observations, we now turn to controlling the structure in the generation process. Given a guidance image and a text prompt as input, we first invert the guidance image to an initial noise using DDIM inversion, which is then progressively denoised using DDIM sampling. During this process, we extract the coarse spatial features and the self-attention maps from the decoder layers of the diffusion model. We then initiate the target generation process using the original inverted noise and the target text prompt. To preserve the guidance structure, we inject the extracted features and the self-attention maps to the target generation. Here are some example results of our method. It can work with minimalistic guidance images. It can handle multiple objects. We can also be creative in translating between diverse object classes while maintaining the guidance structure. We qualitatively ablate our key design choices. As can be seen, only injecting the core spatial features is insufficient for preserving the structure, while injecting spatial features in higher resolution layers results in appearance leakage from the guidance image. On the other hand, only injecting self-attention maps does not preserve the structure as it lacks the initialization of the semantic layout in the core's decoder features. Our final method exhibits fidelity both to the guidance structure and to the target prompt. Our method achieves high-quality results of text-guided image translation in diverse image domains and prompts. Since there is no existing benchmark for such diverse settings, we created two new datasets of text-image pairs. Wild TI2I, which consists of 148 pairs and contains both real and generated images, and ImageNet-R TI2I, which contains high-quality images collected from ImageNet-R accompanied by prompts created using ImageNet-R's renditions and object classes, resulting in 150 pairs. To numerically evaluate the results, we use two complementary metrics. To measure the extent of structure preservation, we use DynoKey self-similarity distance between the guidance and generated images. To quantify the target prompt fidelity, we measure clip cosine similarity between the target prompt and the generated image. As can be seen in the evaluation results on the ImageNet-R TI2I benchmark, our method achieves both high preservation of structure and high fidelity to the target text prompt, while other methods either struggle in structure preservation or in complying with the target text prompt. The same observations hold when evaluating on wild TI2I and generated ImageNet-R TI2I benchmarks. Thank you for your attention and visit our website for more results and code.